Hello, my name is Terry Stewart, and this is part 2 of the Braindrop videos I'm putting together. This one's going to be focusing on the actual design of Braindrop. In part 1, we talked about the background logic that gave us the overall requirements that we would need to put together an analog neuromorphic chip that was capable of being programmed to do lots of different things. And the core ideas that sort of came out of that previous video, all of which was very much based on the neural engineering framework and the approach to neuron programming that's used as part of the neural engineering framework. That led us to this basic idea that we're going to have lots of different groups of neurons. We're going to be feeding input into these groups of neurons. The output from a group of neurons is the weighted sum of its activities. And we're going to be taking the output from a group of neurons and being able to send it to other groups of neurons or back to itself. Fine, that sort of sounds like just totally standard neural network type things. A couple interesting aspects, the weights, the input weights, so the weights between the input and the neurons themselves, don't have to be precisely controlled. We can do better if they are. That's very much related to, in the original days of perceptrons, the plan was you can do this, the first set of feature extraction is sort of randomly, but of course, if you can find features that are more suited to the particular task, then you can do better. But you don't have to. So that's one big aspect. But the output weights, those ones are pretty important and need to be pretty controlled, because that's the main thing you're going to adjust in order to have the network compute something that you want it to do. As far as the neurons and the synapses go, any nonlinear neuron model seems suitable for this sort of approach. You need some nonlinearity, fine. Having internal state in the neuron itself can be useful. And one interesting aspect is if you do have synapses that can be expressed as sort of differential equations or as linear time invariant systems or something like that, then if you can characterize that synapse, then that's going to mean that combined with being able to take the output of a network and feeding it back into itself means that I can now have neural networks that approximate differential equations. So that's sort of the overall hope that we're trying to have here. So how do we go ahead and build that in Braindrop itself? And we're going to be focusing on this diagram as sort of the basic unit that we're building things up out of. And let's just sort of take each part in turn. So we're going to start with the encoder. So this is, in a normal neural network, this would be a set of connection weights that's taken from your input and multiplying by the input, and then you get some set of connection weights. Or some set of connection weights you're going to multiply the input by. You've got some input, some set of connection weights, and that's going to be going into your actual neurons themselves. Okay. How are we going to do that? All right, well, we need a diverse set of weights. What do I mean by that? The whole goal of a neural network, even going right back to when they were originally invented, again, going back to the perceptron days, is that each of these neurons is going to be extracting some feature of my input, and then my output can be weighted sums of those features. Okay. Again, back in like 50s, 60s, the perceptron days, the whole idea was this first layer, they would even refer to these as sort of random connections. The big challenge of, what led to the invention of backdrop was learning, okay, are there ways of adjusting that? But we can start with random connections, because what we want, they need to be random, but they need to be random chosen in such a way that these neurons are each picking out potentially useful features. Okay. So we want these to be random, but also pretty diverse. So when we're doing this in Nengo, when we're doing this in a normal neural network, we can actually say, well, all right, what distribution do I want here in order to give me a good distribution of tuning curves in these neurons? So each neuron is sensitive to different aspects of the input. That's the sort of thing we would want. How are we going to do that efficiently in analog hardware? Well, here's sort of one of the core ideas of Braindrop. Let's just use a resistor mesh. Okay. So this grid down here, those are my actual neurons. We're going to be feeding inputs into this mesh of resistors, and that's going to mean that each of these neurons is going to get some different combination of those inputs. Okay, so that resistor mesh is going to sort of implicitly define the set of connection weights that's going on here. Let's pick this out into sort of a little bit more detail. So terminology, we're going to refer to those points where we're feeding in input, we're going to refer to those as tap points. Okay, so it's a location on the resistor mesh that we can feed input into. And so what we're drawing here is a particular resistor mesh. Each of these squares would be, say, one particular neuron. We're feeding in inputs at the four corners in this particular case. And what are these arrows? What these arrows are indicating is what input goes where. So imagine a case where I've got two inputs. Okay, so I've got two values coming into my network. What I could do, so first of all, we're going to separate out the positive and negative side of each input. Okay, so for each one dimension of my input, I can have both positive numbers and I can have negative numbers. I'm going to separate those out. And I'm going to say for my first dimension, the negative numbers are going to get injected at this point in my mesh. The positive number is going to get injected in this point. For my second dimension, the negative numbers are going to go injected here, and the positive number is going to get injected here. I'm partly separating out the positive and negative just because that's just hardware-wise, it's nicer to separate out positive and negative inputs. You tend to need different circuitry for that. But then it's also the case that this sort of layout is going to give us pretty diverse and effectively pretty diverse connection weights. And that's what we're trying to depict down here. So what we're saying is, in the ideal case where this is a perfect resistor mesh and there's no transistor mismatch, and it's just, okay, any current that I inject at different points in here is just going to smoothly flow across this mesh. If I then take a look at each individual neuron and I sort of say, okay, this neuron here, it's getting input, it's primarily getting, most of its input is coming from this negative first dimension. All right. It's getting some input from the positive side of this first dimension, but it's vastly overwhelmed by the negative input on that first dimension. And for I guess this neuron here, we're sort of getting maybe a little bit of effective input from this one, but not as much from this one. So for that neuron, we can sort of compute, well, what's its effective connection weight? If we'd drawn it as a connection weight, what's the effective connection weight of that neuron? Okay. That's what we're plotting down here. So each of these neurons, so each of these points in this grid is a different neuron. They're color matched. And the reason that they're colored that way is we're actually indicating what's the direction that they end up being sensitive to. So for instance, a neuron, so this neuron here that I was referring to that is mostly sensitive to a negative on the first dimension and isn't particularly sensitive to the second dimension, that would be a point right about here. Okay? The x-axis is my effective connection weight strength on the first dimension, y-axis is the effective connection weight strength on the second dimension. Oops. Okay. If I have a point that's, say, much closer to that tap point, I'm going to get more current, so I'm going to have, that's going to be a point out here. Okay. Similarly, neurons close to this one would be down here, and we're going to get this sort of nice spread of things in between. Now, interestingly, when I do this random generation in Nengo, or in any sort of neural network, if I just do a sort of or the types of random generation that I tend to do when I'm generating these as artificial neural networks, this is the pattern that I want. Okay. I tend to generate connection weights that are randomly distributed all around the unit sphere. And we can transform this top one into this bottom one if each of these neurons has some sort of adjustable gain. All right. So this neuron here, for example, it's far away from a lot of these tap points. It's basically not getting any input. This is ending up to be a kind of a useless neuron. If I had some sort of adjustable gain on that neuron, then I could make it have some, be more useful, right? Even though it's on this resistor mesh. Okay. And so that would be equivalent to moving this point along scaling points out from the origin. Okay, and that's how we can get this bottom graph. You will note that it's not a perfect. If I was implementing this in just digital hardware where I have full control over randomly generating these weights, I would probably want to uniformly sample around this sphere. And indeed, that's generally what we find in biology. This would be often called the preferred direction vector for a neuron. When you measure that in biology, you tend to find a nice uniform distribution. But we're getting pretty close. There's definitely some places where it's not quite uniform, but we can get pretty close with this approach. Similarly, if we have 3 inputs, we can do the same trick. Here again, we have tap points for negative on the first dimension, positive on the first dimension, negative on the second dimension, positive on the second dimension, and then negative on, or I guess positive on the third dimension, and the negative on the third dimension we're injecting at all 4 corners. Again, there's nothing that says that we have to have exactly only one place that we're injecting current. We can have multiple places. This turns out to be a nice distribution for if I have 3 inputs. So I have 3 inputs, I inject it that way, I get this distribution, and again I can turn that into something that's pretty close to sampling having a good sampling of the points on a sphere. Okay. So that's going to be our general approach. And one cool thing to just highlight there is what we've got is we're using this just a purely passive resistor mesh to do this big calculation. Right? Doing connection weight calculations is a really big part of any neural network. Yeah, we're sacrificing precise controllability about what these weights are, but the benefit is that we're basically requiring no power at all to do this, because this is just passive electronics. Cool. So that's our encoder. What are we going to do for a synapse? In a normal biological model, that synapse would be something like, oh, okay, there's inputs coming into these neurons, but then whenever there's a synapse, if a spike comes in, then the actual current being dumped into this next neuron will go up and then decay back down over time. So how are we going to implement that? Well, one fun thing we can do is first of all, we can move that over here. Right? Advantage of, so because the resistor mesh is basically linear, this is a safe thing to do. It's not going to change the behavior of anything. But there's now we have fewer synapses to deal with. Right? Because I now only need a synapse at the places where I'm injecting input. Okay? I only have to put synapses at the tap points, not at the neurons. Okay. These synapses, we do want them configurable. That tends to be something that when we're doing these neuron models, we tend to have a bit of a variability. This is about the range they are in biology. Whether or not that's exactly the right range that we want for sort of engineering applications is another question, but that was about what we were targeting for Braindrop. There is going to be an interesting issue that mismatch means that there's going to be some variability on exactly what the time constant of each of these inputs is. And again, just to highlight what that's saying is that each of these places that I'm injecting input is going to have a slightly different time constant. Okay. That's something that it turns out that you needed to extend the math that I've been showing before about how to convert recurrent connections into differential equations, but it was definitely doable. But anyway, warning, we get a little bit of a complication there. But one really cool thing, the fact that you can have these fewer tap points than neurons, this is very helpful because synapses are actually pretty large. If you want really the possibility of really long time constants, it means you have a very big capacitor. Doing the design for that turned out to be a little bit of a size constraint when we're putting together Braindrop. And what we ended up with was a situation where we have one tap point with that synapse for every 2 by 2, so every 4 neurons. So again, what that means is we can't inject anywhere on this grid, but we just, so it's just every other point, every other row and every other column is where we can inject input. Okay. All right, that should give us a synapse. What sort of input are we going to be feeding into this system? Okay, so I sort of slipped into talking about, oh, well, when you inject a spike, then the input goes up and goes down. Well, hold on a second. Why am I injecting spikes? Why can't I just inject, current as an input? What do I want to do? In general, we're going to design this assuming there's some sort of continuous input that would be the ideal input. Actually, turning a continuous input into current being shoved into a point in a resistor mesh is kind of difficult. So instead, what we're going to do is we're going to take that continuous input and we're going to convert it into a spike train. But now we have the question of how exactly we're going to convert it into a spike train. One option would be, okay, well, I've got this continuous value. Let's just generate a Poisson spike train based on that value. So as the value goes up, so the solid line that I'm showing here is the value I would like to inject. The vertical stripes are Poisson. In this particular row is a Poisson-generated spike train. And then the squiggly line that I'm seeing on top of it, what I'm doing is I'm decoding out that spike train. So because what that spike train is going to do is it's going to cause, cause current to be injected in, and because there's going to be one of these little synapse things, what I'm doing is every time there's a spike, I increase the value, and then I'm decaying it back down again. Spike, decaying back down, spike, decaying back down. Sort of the same process that a neuron would do based on its input. And what we're trying to see is how close, what's the sort of, how accurate is that sort of decoding based on this Poisson spike train. And if we measure that as sort of a signal to noise ratio if you want. And so if we do this Poisson approach, of course, the signal, it's going to depend on how much, what our spike rate is. But for this particular case, here's our signal. We generate a total of 503 spikes, and we've got a signal noise ratio of 10.5. Right, so that's what would happen if we were going to use Poisson spikes. That's not necessarily the best choice. So the difficulty with doing a Poisson input is, well, we're now generating and adding a whole bunch of noise to our signal. Why do that? Let's do something simpler. Let's take that continuous input and feed it into a pure, perfect integrate-and-fire neuron. What do I mean by that? Just integrate the value. Whenever it hits a threshold, emit a spike, subtract back down. Okay, whenever it hits the threshold, emit a spike, reduce my internal value by the same by the amount by the threshold, and then continue. This is exactly the same as an integrate-and-fire neuron. So if you get rid of the leaky term from an integrate-and-fire neuron, then this is just exactly what you would get. And so what we do, and if you do that sort of encoding, and here's as the value changes, now we can say, okay, we get much fewer spikes. Similar signal-to-noise ratio. Well, this is a little bit worse in this example. To sort of also give another point, if we had have used Poisson spikes, and when we were aiming for a lower spike rate, so if we were doing Poisson spikes at a similar spike rate, we would get something like this with a way lower signal-to-noise ratio. So this is how we're going to encode information. We're going to be taking our continuous value, we're going to feed it into an integrate-and-fire neuron. We're going to call these accumulators. They'll come up again later in this talk. But that's going to be the way that we're converting a continuous value into a spike train, and the spike train is going to be what's being injected into the tap points, which is going to go through the resistor mesh, which is going to go to our neurons. We have one more decision to make with this, though. Is, well, hold on, how do we want to configure this neuron that's doing this conversion? In particular, how do we want to deal with positive and negative numbers? So here's one possibility. This black line is the continuous value that we're encoding. All right, and now what I've got is I've got two different spike trains being generated. I've got positive spikes and negative spikes being generated. Why would I want two different ones? Well, if I had have just done one of them, then it would be something like, if I want to represent input values between -1 and 1, so in this sort of case, all right, that would mean that an input value of 0 would be no spikes at all on either side. An input of 1 would mean lots and lots of spikes from one side, not from the other. An input of -1 would be lots and lots of spikes on one neuron, but not the other. Okay. If I had have done something like, let's just have one neuron and have -1 mean no spikes at all, and +1 means lots and lots of spikes, then would there just be this weird asymmetry that we're just sort of, yeah, there'd be a very weird asymmetry that negative numbers being represented in a very different way than positive numbers. So we're not going to go with that approach, but something like this. Another way of depicting this is this plot over here, saying, okay, with different values of x as my input, if I held x constant for a while, what would be the firing rate that would be generated here? Okay, so this is just another depiction of the same plot. Again, this green line is taking those spikes and trying to decode back out, well, what was the original value? By simply, the only thing I'm allowed to do is when there's a spike, I go up or down, and then there's the synapse is causing some sort of decay. Okay. So again, the green line is a weighted sum of the blue and orange spikes with the synapse low-pass filter. And the worry that we would have with this style of encoding is we're really not good at representing values near 0. When we're near 0, pretty much no neurons are firing, and so it's really hard to even distinguish. Are you close to 0? Are you at like 0.1? Like the difference between 0.1 and -0.1 is really, really hard to tell, just because there's no spikes at all in that for those sorts of scales. Right. So that's a little bit of a worry. So another option is to do this. So another option is just to shift my baseline up. Basically, I'm just changing the baseline of firing for these two neurons, such that when they have a 0 input, they have some baseline of, say, 100 Hertz. All right. And then if the value goes up or it comes down, we're going to get different firing rates. Okay. And the intent there is to give me a similar signal-to-noise ratio across the full range of inputs. Okay. Interestingly, this ends up being just something you can just configure in Braindrop. You can do whatever you want, but we were using this bottom in order to sort of calibrate and design the rest of the system. We were using this bottom thing, but again, so this is not something that Braindrop forces on you. Once you have the chip, you can use any of these style of encoding methods. But this bottom one is sort of the intended one that we were thinking of. Cool. All right. So we know everything about our input. We know everything about these weights. What the heck are the neurons going to do? So I'm going to sort of, here's the basic thing that we ended up with, and then I'm going to talk about why we ended up with that. So exponential integrate-and-fire neuron is what we ended up with, just because there was nice, efficient ways of implementing that. And that's what the design team was pretty familiar with. And then we're going to add in some digitally programmable aspects to each neuron. In particular, we're going to add in a programmable gain, and we're going to add in a programmable bias. Okay. So that bias term is going to let me change sort of a background current going into each of these neurons. And then the gain is going to sort of adjust how sensitive the neuron is to firing. Okay. But how in the world why did we do this? Why are we picking these numbers? What's going on here? All right, so let's start by looking at, let's say we don't have any of this control. Let's say we don't have these bias neurons. Let's just take a totally normal neuron model and feed in the inputs based on what we've been describing so far. Okay, and by describing so far, what I mean is, well, look, we're going to be feeding in inputs of this form. We are going to pass those inputs through a resistor mesh by targeting points on the resistor mesh. All the plots I'm going to show so far are sort of the one-dimensional version of this, but similar things are going to happen in higher dimensions. So if I do that, I would, and if I imagined all of my manufacturing was perfect and there was no mismatch whatsoever, I would get something like this. So each of these curves is a different neuron. The x-axis is what the value is that I'm injecting in it right now. And again, I'm sort of holding that input constant for a while and seeing what my firing rate from the neuron is. For neurons that are close to the tap point, I'm going to get something like this line here. So this would be a neuron that is very close to the positive tap point. This would be a neuron that's very close to the negative tap point. This would be a neuron that is far away from the positive tap point, but is closer to the positive tap point than the negative, and vice versa for this one. Okay. So that's what we would get if everything was perfect and all transistors were the same. Here's what happens when we add in mismatch. Right, this is all in simulation. Just sort of, all right, how much mismatch do we expect in that? And we get these curves here. Okay, and the first instinct, it's like, okay, cool, all right, now all of a sudden we have a whole bunch of diverse tuning curves. This is exactly what we want. I've got a whole bunch of neurons that are doing different things for my input. Life is great. One slight problem. Some of these neurons are pretty useless. So for instance, take a look at this neuron here. Okay, across the full range of inputs, that neuron has a pretty linear response. So that means that neuron does not have a significant nonlinearity. The whole point of a neural network is to have the neurons with nonlinearities. That's a pretty useless neuron. Okay. Similarly, this top blue one, I mean, it's got a little bit of a curve there. There's a bit of a nonlinearity there, but it ain't much. The sort of thing we'd really like is a neuron down here where it doesn't respond at all, and then it starts firing. Okay, that's got a nice nonlinearity in it. Okay. And of course, with this diversity, there's also some neurons that just don't fire at all in this whole range. Right. This is what we would like to configure. This is why we're going to start adding in extra terms to configure our neurons. So the way we sort of took a look at trying to plot this is, well, given these curves, you can compute what the effective gain and bias is due to all of this transistor mismatch and everything. Okay, so what do I mean by an effective gain and bias? So let's say there's some ideal neuron tuning curve, right, which is this top one. So that we'll say this blue one, that would be a neuron with a gain of 1 and a bias of 0. Okay, a bias is going to shift this curve left and right, and a gain is going to scale the curve. So I can, just by shifting it left and right, so if I can take this sort of one ideal curve, shift it left and right, shift it up and down, and I can then sort of fit any of these sorts of curves. Okay, so each of these curves I can figure out what its effective gain and bias is. Right, the reason we call them a gain and bias is if we were in a normal traditional neural network, right, they would be a gain at the neuron and a bias at the neuron level. Right, that would just give us these effects. So if we do that, we can plot this curve over here. And then what we're doing with these lines on top of it is down here, so below this line here, is these are all the neurons where the bias is so negative that this neuron just never fires across that window from -1 to 1 of input. Okay. This is a neuron that never fires. Up here, we have a neuron that always fires. So that's a neuron where the tuning curve is pretty flat. Okay. Ideally, what we would like is we'd like neurons that have an intercept somewhere in this range. Right? That's neurons inside this cone. So what we would really like is to have enough configurability, and we have some configurability by moving our tap points around. As we adjust our tap points, that's going to move these clouds around. If we also have sort of a gain and bias term that it can adjust at the neuron, then it turns out that I can reconfigure things and I can sort of rescue a lot of these neurons. Okay? They're still not all perfect. We're still getting a chunk of neurons that are up here that are like, okay, these are neurons that always fire, but fine, they'll still be somewhat useful. We at least won't have neurons that don't fire, and we should have a good range of neurons that start firing at different points. Okay. In fact, we can then go, of course, this amount of mismatch and this amount of variability is going to depend, and how much we can save is going to depend on how many levels of bias I have to control, and on the size of the transistors, because that's going to affect the amount of mismatch that I have. So what we're plotting here is the proportion of neurons that we can save, the proportion of neurons that will be inside that cone as we adjust our transistor size and we adjust our number of bias levels. Okay. And it turns out that even if you stick with pretty small transistors, with 7 levels of bias, I can rescue most of them. Okay. And I get a little bit of diminishing returns as I crank up my transistor size. And then, of course, the fun thing you can do is you can trade off, well, okay, how much area do I need in order to implement these bias levels? How much area do I need in order to make my transistors bigger? But this gives you sort of a target to sort of say, well, my metric is how many good neurons am I going to have? So the eventual design ended up being 7 levels for bias and 4 levels for gain. What we're showing here is here's what the tuning curves, again, this is all in simulation. Here's what the tuning curves would look like without optimization, but then after we optimize setting these gains and biases. And quite honestly, we're just simply doing an exhaustive search across this. Okay. So it's a pretty simple optimization process. Then now all of a sudden we're getting a lot more tuning curves that have good nonlinearities that will be useful for doing function approximation. Given these sorts of neurons, you can now sit down and say, okay, well, what are these neurons? What sorts of, how good are these neurons? Do these neurons now get better at approximating functions? Yes, they do. This is sort of showing, okay, if you have these neurons and if you were just doing the same sort of function approximation that happens in the neural engineering framework in Nengo, that is, look, I have some desired function, I would like some weighted sum of these curves to give me my desired function, right? Then you can go ahead and compute what your mean squared error is for a whole bunch of different tasks. In particular, we're looking at the first 10 singular. So the normal method for figuring out what a group of neurons would be good at approximating is to take these tuning curves and do singular value decomposition. That's going to tell you what these neurons are good at approximating. Okay? And generally what it turns out like is the Legendre polynomials. So the thing that the neurons will be best at is decoding out a straight line. Second best is a linear output. Third best will be an x squared, an x cubed, x to the fourth, but the Legendre polynomials. And then we can actually see, okay, if you use those tuning curves, what sort of mean squared error do you get for decoding out those sorts of functions? And we can see that we get a nice improvement in our mean squared error by having this customizability. Cool. All right, so that's going to be our neuron model. Now we got to go on to our decoder. Because we've now sort of established that math-wise anyway, we have pretty good tuning curves about this first part. Now, how in hardware are we going to do this last part of taking those output from spikes and doing this weight matrix in order to produce an output? So we've got to compute this weighted sum. We've got to have this configurable, because this is the whole point, is we want to be able to adjust these weights in order to change what function this thing is approximating. And we also have this constraint that this output needs to be of the same form as our input, because the whole point of this system is to be able to take outputs and feed them to other things or back to themselves. Okay. So I know what sort of encoding method I need for my output. Right? I need these sorts of, spikes of this sort of form. How am I going to do that? Well, we're going to do it digitally. So this is why Braindrop is a sort of a hybrid analog digital system. We're just going to do this as a digital accumulator. Okay. the same thing we were sort of using to produce these spikes, to produce our input. We're going to make this tiny little, so you can think of this as a digital neuron, or a non-leaky integrate-and-fire neuron, right, that produces positive and negative spikes. So it's got some internal state. Whenever a spike happens, we add the weight associated with that spike. If our total value is now greater than 1, I emit a +1 spike and subtract 1 from my internal state. If the value is less than -1, I emit -1 as an output and add. Okay. And of course, in practice, we ended up doing this in, I've forgotten how many bits. It's either 8-bit, I think it's 8-bit fixed point. I think that's what we ended up with. I would need to double check that. But that is our approach, and that will end up producing spikes that are of exactly the same form as this, because then we just make sure that when we solve for the decoders, when we solve for these connection weights, we solve for the connection weights that will produce the pattern of spikes that we want. It will produce the target values that will produce these patterns of spikes. Cool. The last tiny little bit is to say, okay, well, how do we route things between things? For that, I've got, I'm not really sure how much detail to go into this. Here's sort of the overall routing diagram that happened with Braindrop. What we're looking at here is spikes coming into the system, going through the synapses, going through the diffuser mesh, going into the neurons, spikes coming out of that. And then we come in, that comes into the digital part of the system, where these spikes come in. We go look up our weight memories. If it's a weight memory, that's what is storing these decoder weights. That ends up adjusting the accumulator memories. That's the internal state of these accumulators. Okay. The output spikes from that can then end up being routed either to other cores or back into, we also set it up such that if you want to, you can go back and run it through another set of connection weights. So you could actually chain just another set of connection weights and then another set of connection weights. But eventually you can fire it off back to another analog component and go feed it through. So that's the basic approach. So, attempt at doing an overall summary of what this ends up looking like. On the left would be the sort of the traditional standard Nango approach, where I would have neurons, they're producing spikes. Those spikes are getting multiplied by connection weights. So that means I now have sort of, they're getting multiplied by connection weights and then being summed. So that would mean that I would, the actual input that might go somewhere else is the sort of these weighted spikes. Really want to think about what's actually happening. You can, of course, in Nango, you can optionally have another transform matrix. Whenever you make a connection in Nango, you can put another transform matrix on there. That's just another matrix that you can either think of this as getting multiplied and rolled into the decoder, or you can think of it separately. Same trick. So you can have another transform matrix in there that would just multiply it again. Again, we did a set of weights. And then those weights would then get multiplied by encoders and then go into a synapse and then get fed into neurons. That would be sort of a traditional-ish approach of doing connection weights. If this was like totally traditional neural network, then this whole block here could be thought of as just one giant connection weight matrix. The only thing that's different between that and this is that one giant connection weight matrix has been factored into 3 parts: the encoder, a transform, and a decoder. Okay, but other than that, it's the same conceptual idea. This tends to be how we implement it in digital hardware a lot, just because these sort of operations are the sort of matrix multiplies and whatnot that digital hardware tends to be suited for. In Braindrop, the process is slightly different. Here we have our neurons, our decoder weights. That's going into the accumulator. All right, we're going to do that multiplication. Out of the accumulator, we're going to get spikes. In each of these spikes, there's no longer this magnitude issue going on here. These spikes are the same size. The magnitude is being encoded in the timing between the spikes. That also means, so because all of these spikes are all the same magnitude, Now this means that my synapse logic is nice and simple. So I only have to be able to inject pulses of the same size. We do end up having some, it's kind of nice if you can have somewhat linear, but not required. Anyway, both having your positive and negative spikes be somewhat similar sizes, but definitely not required. But we get these spikes, feed those into the synapses. That goes into through the resistor mesh, which is, we could kind of be thinking of as doing some sort of convolution with the some sort of spreading kernel. And then that's going to be the input that's going to go into the somas. So that's an attempt at sort of a high-level summary of everything I just said. Cool. That's the core ideas. For more information, this is the main paper that sort of gives an overview of the system and its results. This is Alex Necker's PhD thesis, which goes into lots and lots of detail. And then this is a paper specifically on the aspect of optimizing the gains and biases and choosing the number of bias bits in order to give good tuning curves. And pretty much all the diagrams I was showing are out of these 3 papers. Great. Thank you so much. I hope that was, yeah, so that's the core ideas behind Braindrop. And I hope that gives sort of, yeah, a sense of the various different things that we had to do in order to design that. Thank you.